Hello, my name is Steve Miller, and I'm the Technical Marketing Manager for the Simscape product family at MathWorks. In this presentation, we're going to see how you can simulate fluid power systems with Simscape Fluids. Here are the key points from this presentation. First, we're going to see that Simscape Fluids provides libraries of component models for fluid power systems. You can assemble a physical network with hydraulic actuators, valves, and other components, and use that to model fluid power systems, such as a backhoe arm. The models you build can be customized to exactly meet your needs. You can create reusable assemblies from the blocks that we provide, adjust parameterization to include or neglect physical effects, and you can define custom components, and we'll see how you can leverage MATLAB and Simulink to perform many common simulation tasks, such as system-level analysis, where you wish to optimize the integrated mechanical, hydraulic, and control systems, testing those control systems, including tests using hardware-in-the-loop testing. Here's the agenda for our presentation. We will first look at an example application and examine some of the tasks you can perform. We will then assemble a model of a hydraulic actuation system. We will refine that model by adjusting fidelity and customizing a component with the Simscape language. We'll then optimize the system-level design and use hardware-in-the-loop testing to test the control system. Simscape Fluids is used in a number of industries to model fluid power systems. An example of an application is a backhoe with multiple hydraulic cylinders. Modeled in Simscape Fluids, the hydraulic network will consist of many components, including a pump that supplies pressures to all of the actuation systems, valves controlling those actuators, and a control system that tracks the reference position. Simscape Fluids is used to select the hydraulic components, for example to size the actuator that will be used, to test system integration, seeing what happens when we combine the hydraulic system with a three-dimensional mechanical system, and to design the control system for this backhoe, including hardware-in-the-loop testing. Here is our model of the backhoe arm. We can see that it consists of three actuators that raise and tilt an arm and a bucket. When we run the simulation, we can see how the system performs. This 3D animation provided by Simscape Multibody shows how the system moves. If we look at this scope, we can see how the system behaves. The control system is attempting to track reference angles, and we can see that it is tracking the reference angle in pink fairly well. Going into this subsystem, we can see how Simscape Fluids is used to model the hydraulic network. We can see a pump, pressure relief valve, and physical connections that connect all of the three hydraulic actuators together. The actuators themselves consist of a hydraulic cylinder and a directional valve. And the directional valve model has a number of different parameterization options so that you can use your measured data or data sheets to get accurate values for the system. Simscape Fluids also provides a library of hydraulic fluids. This database includes many common hydraulic fluids, and you can assign a few of the parameters that are necessary. And you can add your own fluids to the database if it doesn't have what you need. Connecting this hydraulic network to a model of the three-dimensional mechanical system in Simscape Multibody allows you to test your hydraulic design with the realistic load to see how the system behaves. And combining this with a control system allows you to use simulation to test and optimize the system-level design. The entire model can be converted to C code. This allows you to test your embedded hardware and software against a real-time capable model of the plant, so that you can verify that the embedded software and hardware will behave as designed. We are going to model a backhoe actuation system. The system that we will model will consist of three actuators to raise, reach, and tilt the bucket. A control system controls the movement of a spool inside a valve, and the position of the valve determines whether hydraulic pressure will be applied to one side or the other side of a double-acting cylinder. This will control whether the cylinders will extend or contract. We have a number of tasks that we wish to use simulation to perform. We want to determine the required size for the actuator components, the cylinder, the valve, the pump, and others. We want to use simulation to optimize design parameters in the actuator and in the control system. We would like to use simulation to measure the robustness of the design with relevant physical effects, such as hydraulic forces within the valve. And finally, we would like to use our simulation to test embedded hardware and software using hardware-in-the-loop testing, where a virtual model of the physical system is used to test the embedded hardware and software. In this demonstration, we're going to see how to model a hydraulic actuation system using Simscape Fluids. In our model of the hydraulic actuation system, the spool inside this valve controls the flow of pressure from a pump to either side of a hydraulic cylinder, which can extend and contract. A motor will drive the shaft of the pump, controlling the speed, and a control system will adjust the position of the valve. We will model this system within the Simulink environment using Simscape Fluids. The model we build will look like this, and we'll see when we run our simulation that the piston goes over its entire range of travel. We will then connect this to a realistic model of a three-dimensional mechanical system to see how it behaves. I'll now switch over to the model so you can see how this is done. To start, we will enter the command sscnew into the MATLAB command window. This will open up a Simulink model with the settings recommended for Simscape models. The first thing that we'll need to add into our system is a pump. I will click in the diagram and type in the word pump. Here I can see a list of the pumps I can choose from, and I will select a fixed displacement pump. I can specify the pump displacement here. Our pump needs to draw fluid from a tank. We will use a hydraulic reference to represent that. I click and drag to create an ideal hydraulic connection, type in reference, and here I have an ideal hydraulic reference which will represent our tank. To control the flow of fluid from the pump to the hydraulic actuator, we need a directional valve. I'll type in 4 and select from one of the directional valves that are available. Double-clicking on the block, I can go in and specify the different parameters. There are multiple parameterization options, so I can select the one appropriate for the datasheet that I have, or I can use one that's appropriate for measured data. I will increase the size of this valve to make it commensurate with the pump, and leave the rest of the settings as they are. I will connect the P port of our valve to the high side of the pump. We need to limit the pressure coming from the pump. We will use a pressure relief valve to do that. I will right-click and drag to create a hydraulic branch, and then type in relief valve to get the component. Double-clicking on this block, I can also change these parameters, and I will adjust them to make them commensurate with the size of the pump and valve that we are working with. I'll connect the low side of the relief valve back to our tank. I'll also connect the low side of our hydraulic directional valve to our tank as well. Next, we'll add our hydraulic actuator. I will click and drag to create a hydraulic connection and type in cylinder. Here we can see the different cylinder components that we can use. I'll place this component in our network, create the additional hydraulic connection, and then double-click on the block to set the parameters. We'll need to make this actuator a bit bigger to handle our backhoe arm. We'll change the piston stroke to match our design for our system, and we will change the hard stop parameters. These two mechanical connections represent the mechanical connections from our cylinder. We will connect this point to a point fixed in space. The other side is the rod which is connected to the piston in the cylinder. We wish to have this act against a mechanical load. We will click and drag to create a mechanical connection and then add a translational spring. We want the cylinder to act against a spring damper, so we will click and drag and also add a translational damper. And we'll attach this side to a point fixed in space. To specify the inertia of our load, we will click and drag and add a mass block and set the mass to be 100 kilograms. Our physical system is complete, but we still need to specify the inputs to our system. One input is to our pump. We will click and drag to create a mechanical connection. We will insert an ideal angular velocity source in order to spin our pump at a fixed speed. The other side of this source we will attach to a point fixed in space. We will specify the speed of our pump using a constant block. And we will specify it to spin at its rated speed of 188 radians per second. Because Simscape and Simscape Fluids use solver technology above and beyond what is available in base Simulink, we will need access to additional settings. These we can access in the solver configuration block. The remaining input to our system is the position of the spool in the valve. We will specify that using a Simulink signal. We need to specify the units of that signal, and we will use this converter block to do it. Here we can specify the units of the signal to be in meters, or the displacement of the spool inside the valve. To make the piston move over its entire range of travel, we will use a sine wave as an input, and we will specify the amplitude to be 3 millimeters. The last thing that we will do is specify the hydraulic fluid, so we will click and drag to create a branch, and you insert a hydraulic fluid block. Here's where we can specify the type of fluid and specify any of the other relevant parameters. With this, our hydraulic network is complete. The last thing that we'll do is ensure that Simscape logging is enabled. Here in the configuration panel under the Simscape pane, we can enable Simscape logging. We can also set other settings in order to configure how it is saved. Now we can run the simulation, and then right-clicking on any block, we can access the Simscape Results Explorer. Here we can see a tree browser that shows all of the simulation results. Because we right-clicked on the translational spring, we can see different values, including the distance that the spring was compressed or how much the piston moved. We see that it moved over its entire range of travel of 0.5 meters. We can also see the amount of force that this actuation system can provide. We can also explore hydraulic quantities, such as the pressure that the pump needs to deliver. We are satisfied with how our system behaves with this very simple load. Now we will add a more realistic load. We have built up a model of a three-dimensional mechanical system, the bucket and the arm, on our backhoe. Connect the mechanical connections here, and then connect the output of the subsystem we've put together to a Simulink scope block. Now when we run the simulation, we will see a 3D animation of the mechanical system. So we can see that our actuation system is moving the bucket back and forth. When we look on the scope, we can see that our system is moving over its entire range of travel. And when we go into the model of the Simscape Multibody system, we can also explore quantities using the Simscape Results Explorer. Here we can see the kinematic quantities of the specific joint. In this demonstration, we have seen how we can model a hydraulic actuation system using Simscape Fluids. We need to make sure that the components we are using in our model match the behavior we are going to get from the actual components in our system. Next, we'll see how to use optimization algorithms to automatically tune models to match measurement data. In this demonstration, we're going to see how we can estimate model parameters using measured data. We have a model of a hydraulic actuation system. When we simulate the model with these inputs, these are the results that we get. However, data from a hardware prototype looks like this. We can see that our model does not match reality. It is likely because there are parameters of our system that are not correctly entered into our model. We may not have that data from the datasheet, or they may have become altered over time. We could tune these parameters by hand, but a more efficient way would be to use optimization algorithms to tune them automatically. Using optimization algorithms, we can automatically tune these parameters until the results of the simulation match the measured data. Here are the steps that we'll go through. First, we will import the measured data. We will then identify the parameters we wish to tune and their ranges. Next, we will estimate the parameters. I will now switch over to the model so you can see how this is done. Here is our model of a hydraulic actuation system. A hydraulic valve controls the flow of pressure from a pump to a hydraulic cylinder. This input signal controls the movement of the spool. When we run the simulation, we will see how it performs. On this scope, we see the input signal, and on this scope, we see the position of the piston. The yellow line are the results of the simulation, and the pink line are results from a hardware prototype brought into our model here. We can see that they do not match. We need to adjust parameters in our model to make it realistic. The parameters that we are unsure of have been defined as MATLAB variables. We will automatically tune these variables to make the results match. To do this, we will use Simulink Design Optimization. I will click on this link, and this will open the Simulink Design Optimization tool. The steps that we need to perform are: first, we need to import the measured data. Here you can see the position of the piston that we measured from the hardware prototype and our input signal. The next thing we need to do is to select the parameters and their ranges. Simulink Design Optimization has detected the MATLAB variables in our system, and here we have specified the valid ranges for these variables. Again, we can't let the piston area go negative. That wouldn't be physically realistic. Now that we have done these two steps, we can now estimate the parameters. During the estimation, Simulink Design Optimization will automatically run the simulation, compare the results of the simulation with the measured data, detect the sensitivity of the parameters to changes, and then rerun the simulation. With each test, changes are being made to those values that are hopefully bringing it closer to the values and minimizing that cost function. You can see that each of these iterations are being done automatically. So even if I knew exactly the set of variables that I wanted to test, I couldn't enter them in manually and run the test as quickly as this is going. The other aspect of this is that because Simulink design optimization can detect the sensitivity of the results to the different parameters, it will be able to make a much better guess and estimate as to what the value should be than I would be able to do simply by looking at the plots. Even after a short period of time, we can see that the results of the simulation are much closer to the measured data. We could speed this process up even further by running the simulations in parallel. It is currently configured to run them sequentially or one after another so that you can see the individual iterations. However, it would be possible to configure this entire estimation to run in parallel, and that would accelerate the entire process. I'm going to stop the estimation now because you can see that the results are quite close. But if we did let it continue, it would continue to minimize that cost function until these traces were as close as possible. In this demonstration, we have seen how we can use optimization algorithms to automatically estimate model parameters. Now we'll take a look at some of the options for refining your model in Simscape Fluids. There are a wide range of components available in Simscape Fluids for your fluid power system models. We'll take a look at a few of them here and the options that they offer for adjusting fidelity. There are a wide range of actuators in Simscape Fluids, including both translational and rotational actuators. You can add or neglect compressibility in these components depending on the needs of your simulation. There are various mechanical effects available in these components, such as hard stops, friction, and additional forces, and you can also include thermal effects, including the effect of temperature on the fluid properties and heat transfer to the environment. There are many more components available in the libraries than what you see here. There are valve libraries dedicated to various different tasks that you will find in hydraulic systems. Directional valves are available, including spool valves, check valves, and cartridge valves, with various parameterization options. These parameterization options help you leverage data from datasheets or measured data from a real system. There are also pressure control valves, those appropriate for control tasks where the throttle is variable, and those for switching tasks where the throttle is fixed. With these, you can also adjust whether or not the opening dynamics are included or neglected, again based on the needs of your simulation. There are also a range of flow control valves, those where the flow is pressure dependent and those where the flow is pressure independent. You can see the entire list of valve components by looking at our web pages. In the Pumps and Motors library, you will find both fixed and variable displacement machines. These are appropriate for gear pumps, vane pumps, and piston pumps. You can also combine components to create custom pump designs. Each of these has a wide range of parameterization options for pump delivery, efficiency and losses, leakage, and friction. Looking at the pipes and tanks libraries, you will find that the pipeline models are highly configurable. You can add or neglect fluid compressibility, fluid inertia, and wall compliance. You can also incorporate effects such as elevation changes and heat transfer into your pipeline models. The tanks and accumulators allow you to adjust the method in which you parameterize the volume, the number of inlets, and the pressurization. If we take a look at the heat exchangers, it includes both standard and custom types. You can configure them for parallel or counterflow, single or multiple shell passes, and you can also configure it for mixed or unmixed flow. You can parameterize the pressure losses and the heat transfer according to a number of different correlations, and you can also add or neglect fluid dynamic compressibility. A wide range of components is available to you in Simscape Fluids, and you can combine these blocks together to create reusable subsystems that implement even more complex components. In our next example, we will see how we can combine these blocks together to create a custom servo valve. In this demonstration, we're going to see how you can model a custom four-way valve using Simscape Fluids. Simscape Fluids provides a four-way directional valve block. This four-way directional valve block approximates much of the dynamics you would find in a four-way directional valve. We would like to create a more complex model that models these effects more explicitly. The structure of the valve we wish to model looks like this. It has the same connection ports to the pump, tank, and A and B ports. However, the spool dynamics are included. An electromechanical actuator controls the flow of hydraulic fluid within the valve so that the hydraulic pressure moves the spool. When the spool moves, it connects the tank to the B port and the pump to the A port. It can operate in both directions. We would also like to include the effect of hydraulic forces in our valve model. As the hydraulic fluid moves past the orifice, it creates a hydraulic force that will act to close this opening. We would like to create a model that incorporates all of these effects within the Simulink environment. We will use Simscape Fluids to do it. The structure of our valve will look like this, and we will see that we can enable and disable forces within the valve. Using simulation, we will be able to see the effects those forces have on valve and system performance. I'll now switch over to the model so you can see how this is done. Here is our model of a hydraulic actuation system actuating the bucket on a backhoe arm. When we run the simulation, we can see how the system behaves. We can see that the bucket is moving back and forth in this three-dimensional animation provided by Simscape Multibody. Here in this plot, we can see how the bucket angle tracks a reference signal. We would like to explore the behavior of the valve, including trying different types of valves and the effects of hydraulic forces on the valve. Currently, we are using a very abstract version of the four-way valve. If we go underneath the mask, we can see that the variant of the valve that we are using uses the four-way directional valve provided by Simscape Fluids. The dynamics of the valve are abstracted out to this valve actuator block. In the mask for our component, you can see that the parameters for the valve actuation dynamics are simply a gain, a time constant, and a saturation. We would like to explore a more complex version of this valve in order to assess the effects of the type of valve and hydraulic forces on it. So we will go back to our mask and activate a different variant for our valve, namely the version with a flapper nozzle and a centering spring. So now we can see that a different variant of the model is now active. This is using variant subsystems. When we go into this subsystem, we can see how the model has been created. The flapper nozzle, shown here in yellow, has been modeled using these yellow blocks, the inertia, spring damper, and hard stops limiting the flapper's motion. These arrows represent the hydraulic passages where the fluid comes in and the hydraulic pressure can move the spool. These hydraulic passages have been modeled using these orifice blocks. The hydraulic passages that activate the spool are modeled using these lines. Going into this subsystem, we can see the mechanical model of the spool, as well as the subsystem that has the connections between the pump, tank, A and B ports. Going into this subsystem, we can see that we also have different variants here. A variant that neglects the forces due to the flow of hydraulic fluid, and a variant that incorporates them. Looking in here, we have created this model using standard orifice blocks to model the passage between the pump A, B, and tank ports. Going back up a level, we see that there is another variant that includes those forces. So if I go to the spool tab, which is now active since our model has spool dynamics in it, we can enable the hydraulic forces. Now if I go into this subsystem, we can see that the structure is the same, but instead of simply using the variable area slot block, we have also included a block that will apply the force back to the spool, again including the effects of these dynamics. We would like to test the effects of hydraulic forces on this type of valve. To do that, I'm going to use a MATLAB script. This MATLAB script will test this valve under two conditions. One condition where the hydraulic forces are not included, and then the other variant where the forces are included. At the conclusion of the simulation, we can see an array of plots have been produced. We can see the spool force was active in the second run. This one compares the two runs with and without the force. We can see that when the force was active, the bucket cannot react as quickly to the commanded signal here in black. We can see that the forces affected the spool position. It couldn't open as quickly. And we can see that that affected the pressure in the cylinder. So using a MATLAB script, we were able to automate these tests and produce results showing the difference between the two. We can also automate the test to compare the different types of valves. So I will disable the hydraulic forces and use another MATLAB script to test all of the different variants of the valve models. We're starting with the abstract model. Then we'll move to a variant that just includes the spool dynamics, no flapper nozzle. And here you can see the results. So all of the four valves have now been compared. We can see how the type of valve affects the behavior in the system. In this demonstration, we have seen how we can model a custom four-way valve using Simscape Fluids. We have seen that there are a wide range of options for customizing a Simscape Fluids model. We will now show how you can create your own custom component. In this demonstration, we're going to see how we can use Simscape language to define a custom hydraulic component. We are modeling a hydraulic actuation system. We would like to use custom equations to define the relationship between flow rate and pressure at the entrance to each of the hydraulic chambers in our hydraulic actuator. To do this within the Simulink environment, we will use Simscape language. The component we create will look like this. It will have two hydraulic ports for this orifice. Looking at a portion of the Simscape language code, we can see that the code is MATLAB based, it's object-oriented, and allows us to define implicit equations, which can include DAEs and ODEs. I'll now switch over to the model so you can see what this looks like. Here is a model where we can test our custom hydraulic orifice. When I run the simulation, we'll see how it behaves. Here you can see the pressure drop across the orifice, and you can see that as we increase and decrease the flow rate through it, there are two regimes, a laminar regime and a turbulent regime. Double-clicking on the block, we can see the source code. If we go to the bottom of the source code, we can see the custom equations that we have implemented to get the behavior that we need. I will go through this code in more detail in PowerPoint, but before I do that, let's incorporate this orifice into our actuation system. Here is the actuation system we've been working with. If I run the simulation, we will see how it behaves. We can see how the piston is moving between the hard stops. We want to use this component to customize the behavior of the fluid at the entrance and exit to this cylinder. So I'll go back to this model, grab our custom orifice block, drag and drop it on the line, and it will connect right in. Now I can rerun the simulation, and we'll see how the system behaves. We can see that adding in this custom orifice has changed the behavior, and this is what I was looking for. I'll now go back to the slides so I can explain to you how we've created this custom component. This is the source code that implements our custom hydraulic orifice block. The first portion of the code is where we define the hydraulic ports. Our orifice needs to have two ports. We reuse the domain definition from Simscape so that our block is compatible with the rest of the hydraulic libraries. The next thing we need to do is to define the user interface, where we expose the parameters we want other users to adjust. This is done here. You can see that in this section of the code, we have defined the parameters that we will use in the equations, the default values, and the units. We've also defined the prompt that users will be shown. In the next portion of our code, we will leverage MATLAB. Here you can see we have used MATLAB code to verify that parameter values are legal, and we have done some preliminary calculations. In the next section, we define how this component will behave. Here are the custom equations we wanted to implement, and here's what the code looks like. The most important thing to note about this section is that these are simultaneous equations. All of these equations will become part of the overall network in Simscape, and all of these equations will be evaluated simultaneously. This is different than what you may be used to in MATLAB, C code, or even in Simulink, where the blocks or the lines of code are executed one after another. We have defined a set of implicit equations here, and all of these equations will be solved simultaneously. We are not assigning different values here and then using those values in the next line, and we're not specifying inputs and outputs. The equations you define here can have branches with if then else. You can turn on or off zero crossings. The equations you define can be based on variables, their time derivatives, parameters that you define, and other quantities. In this demonstration, we have seen how we can use Simscape language to define a custom hydraulic component. Now that we have seen many different ways to define and tune the model of the physical system, we'll now take a look at some capabilities for optimizing the system-level design. In this demonstration, we will see how we can optimize the performance of a hydraulic actuation system. We have a model of a hydraulic actuation system in a backhoe arm. A control system adjusts the position of a spool inside a valve to track a reference signal. When we evaluate the design in simulation, we can see that it is well within the requirements for the force the actuator can provide, but it is not meeting the requirements for tracking a reference signal. We need to optimize our design so that it meets each of these requirements. To do this, we will use Simulink design optimization. We will apply optimization algorithms to parameters in our control system. The optimization routines will ensure that the final design meets the requirements that we have. I will now switch over to the model so you can see how this is done. Here is our model of a hydraulic actuation system connected to a three-dimensional mechanical model of a bucket arm. When we run the simulation, you can see in this 3D animation provided by Simscape Multibody how the system works. As the cylinder extends and contracts, it angles a bucket. Looking at this scope, we can see that our system is not tracking the reference angle very well. Looking at this other scope, we can see, however, that the force applied by the actuator is well within the limits that we have specified. To improve this situation, we need to tune parameters in our controller. They have been defined as MATLAB variables. We could tune these parameters by hand. However, a more efficient method would be to use optimization algorithms. We are going to enable fast restart to accelerate the tuning process, and then open up Simulink Design Optimization. Here you can see that we have defined the requirements for our system, the reference angle that the system must track, and the limits on the force that the actuator can provide. Simulink Design Optimization can also see the MATLAB variables that we have defined, and we have already set the minimum limits for these parameter values. Now, we will run the optimization. During each step of the response optimization, Simulink Design Optimization will run the simulation, see how far we are away from the requirements, assess the sensitivity of the parameters to the simulation results, and then change those values and rerun the simulation. You can see that the optimization is proceeding very quickly. Even if I knew exactly which parameters I wanted to change, I wouldn't be able to change them this fast. And we can see that it is doing a very good job at assessing the sensitivity of the parameters. As you can see, it is converging on a much better result very, very quickly. Even after this short period of time, we can see a very dramatic performance in how well the system is tracking the reference angle. And you can see we are still within the limits defined for the force. Right now, we're running this optimization sequentially, one run after another. However, we could accelerate this even further by using parallel computing. We could send these set of tests to separate cores on a machine or distribute them across a computing cluster. You can see that in a very short period of time, Simulink Design Optimization has found a much better set of parameters that are meeting our requirements quite well, tracking the reference signal and staying within the limits that we have defined for the force the actuator can provide. In this demonstration, we have seen how we can use optimization algorithms to optimize the design of our system. Now that we have created our model and optimized the design, we will now see how we can use the model to test embedded hardware and software in hardware-in-the-loop testing. In this demonstration, we will see how to configure a Backhoe model for hardware-in-the-loop testing. We have a model of a hydromechanical actuation system built in Simscape Fluids and Simscape Multibody. We are satisfied with the performance of our simulation on the desktop. We now wish to configure it for hardware-in-the-loop testing. However, portions of our model are numerically stiff. We will need to configure the solvers so that it is real-time capable and convert it to C code so that we can use it in real-time simulation. We will use the Simscape local solvers and Simulink coder to do this. Here are the steps that we'll go through. First, we will configure the model to use a fixed-step, fixed-cost solver, appropriate for hill testing. We will rerun the simulation on our desktop to verify that we get the same results. We will then convert the model to C code and download it to the real-time target. Once it's there, we will rerun the simulation to verify that we get the same results and that we don't have any overruns, that the simulation is running fast enough. Finally, we will be able to run our test. We will vary a parameter in the physical system and see how the control system reacts. I will now switch over to the model so you can see how this is done. Here is the model of our backhoe arm. Inside this subsystem, we can see the physical model of our system: mechanical parts, joints that define how they move, and 3 hydraulic cylinders, where each cylinder contains a double-acting hydraulic cylinder controlled by a directional valve and friction. When we run the simulation, we can see an animation of the simulation results provided by Simscape Multibody. Here you can see the backhoe arm with its 3 actuators, the 3 hydraulic cylinders that we saw in the other model. And during this 30-second simulation, we can see that it extends the arm and then tips the bucket. If we look at the scope showing the results of the simulation, we can see that it tracks 3 reference signals fairly well. We are happy with the results we're getting from this model in desktop simulation and now wish to configure it for hardware-in-the-loop testing. To do that, we'll use this MATLAB script to go through the steps. First, we need to run a simulation with the variable step solver to obtain a set of reference results. We need these results in order to know that when we've configured it for fixed step simulation, that the results we get are accurate. Now that we have these results, we will add them to a plot. We are now running a simulation with a fixed step solver. We've configured it to have the global solver of ODE1, and if we go into the model itself, we can see that we have also enabled the Simscape local solver. So we've enabled the local solver here, and we have selected fixed cost simulation. This means we are limiting the number of computations per time step. This will help us avoid overruns on the real-time system. At the conclusion of this simulation, we will upload these results and add them to our plot to verify that with the settings we've chosen that we are still getting accurate results. So our simulation has completed. We will overlay those results on our reference results, and we can see that we get a very accurate response using the fixed step solvers. It matches the reference results almost exactly. Now we will configure our model to have runtime parameters, parameters whose values we wish to change on the real-time hardware. In this model, we are going to, the test that we are going to make on the real-time hardware is to see what happens when the cylinders age. Aging hardware is not always easy to find and can be difficult to configure. However, in a simulation, we can do that quite easy. We're going to test the case where one of the seals has failed or has gotten worse over time. So we're going to change this friction coefficient. So we have configured it to be a runtime parameter. Again, we can change its value on the real-time system without regenerating C code. Now that we have configured our solvers and selected parameters we wish to tune, we can generate C code from the model. Once the C code is generated, we're going to download it to this machine, which is our real-time operating hardware, and here you can see a monitor where we can monitor the results of the simulation. If I switch over to the MATLAB window, the MATLAB command window, we can see messages from the production of the code that's going on to our real-time system. So you can see the C code has been generated. It is now on the real-time system. We will switch to external mode so that we can monitor the simulation on our Simulink scope. We will then connect to the target and run the simulation. So the simulation is now running in external mode. You can see the results of the simulation on the monitor, and they are synchronized with the results you can see on the scope. So you can see that the signals are moving down together. At the conclusion of this 30-second simulation, we will upload the results from the real-time hardware and overlay them on the results that we have gotten from the previous runs. This is to verify that we are getting, again, the same accurate results, and we'll also see if we make it through the entire simulation without any overruns. So the simulation has completed. We will upload the results, and we can see they match the results from our previous test perfectly. Now what we'll do is we will run the test where we're going to see what happens after the seals degrade over time. Using the commands getParam and setParam, we are adjusting a friction value on the real-time hardware. We'll now rerun the simulation with this adjustment to the physical model. This is what you would do in a hardware in the loop test, where you want to verify the behavior of the embedded hardware and software when the behavior of the physical system changes. Okay, so we have reached the end of our 30-second test. We will now upload those results and see what it looks like when we compare it to the other ones. And we can see that the results are different, so our parameter change did have an effect on how the model behaves. So we could use this model to test embedded hardware and software in a hardware-in-the-loop configuration. In this demonstration, we have seen how to configure a Simscape model for hardware-in-the-loop testing. Here are the key points that I want you to take away from this presentation. First, Simscape Fluids provides libraries of component models for fluid power systems. You can customize your models by creating reusable assemblies, adjusting the parameterization of the components, and defining custom components, And finally, you can leverage capabilities in MATLAB and Simulink to perform system-level analysis, design control algorithms, and perform hardware-in-the-loop testing.